Hi, I'm Mike McManus. I'm the Director of Precision Medicine at Intel, and I'm joined here by two collaborators. The CEO of Clovertex, his name is Kshitij Kumar, and Professor Toshio Maria. And before we get started, just wanted to say if you have questions, if we can hold them towards the end and just shout them out and we'll deal with them. And if you have questions, like deeper questions, there's a session at 2 o'clock here in Caesars Forum where you can come talk to us one-on-one and ask whatever you want. So before we get started, I had no idea like the audience composition here. So let's see if that worked. Come on. So yes, I wanted to just explain what cryo-electron microscopy is. It's for those of you that know what it is, well, sorry. For those of you that don't, maybe you'll find it interesting. But basically, on the slide here, actually I'll point this way, what it is it's a method for going from, say, a mixture of protein of interest that's sitting in water, and you can't really crystallize it and use traditional methods to understand its three-dimensional structure, so you freeze it. That's where the cryogenic comes from in cryo. And then once it's frozen, you bombard it with a bunch of electrons and a beam that comes from a microscope, and that's where the EM comes from, electron microscopy. And you get a bunch of blurry images, and for those of you that remember what TV was like when things went off the air, it looks like static. But there's actually information in those images, and the software tools, there are several, take that data and convert it into a three-dimensional model. In this case, it's a spike protein from COVID-19 that you can manipulate with a computer. And then from there, you can go on and do other computational tasks. So that's what Cryo-EM is. That's what this first 30-minute section is about. So I've introduced these guys. Again, so he is from a company called, Kshitij is from a company called Clovertex, which is a combination of IT services cloud company. And Professor Maria is from KEK, and we're going to let them each talk about their company now. So Kshitij, why don't you start?
Thank you, Michael. Can I get the pointer here? Thank you. Myself, Kshitij Kumar, founder of Clovertex. Very happy to be here with Professor Moria and Michael. How many of you listened to the session in the morning, the keynote session, or attended it? Because I was very happy to see that there was so much focus in that session on high-performance computing as a technology area, but then so much focus on drug discovery, multi-omics, healthcare, because that's the area where Clovertex really specializes in. In fact, a lot of HPC services that they talk today, they came around 2018, 2019 timeframe. And at that time, those services were not what they are today. Some of them were very immature, some of them were in a preview state, but that was a time when Clovertex started in 2018 with an idea that, hey, can we really reduce the drug discovery time to save the patient lives? It sounds like a very interesting statement, a very interesting moniker, but as technologists, what we can do? Like, it's a lot of science. Drug discovery is all about science, clinical trials and all, but can we provide enough of right kind of compute to the scientists? Keep the scientists shielded away from all the complexities of the cloud and infrastructure to help them focus on science. And little did we know that in 2020, we will actually see the results of that, unfortunately, through the COVID pandemic. So in 2019, we were engaged at a large pharma where we built their research platform in AWS using high-performance computing services. And in 2019, of course, we didn't know about COVID, no idea what's going to happen. And in 2020, when the lockdown happened, when COVID became like a global event, this pharma company was able to leverage their research cloud in the AWS, be it getting several compute instances, hundreds of them, be it providing scientists lots and lots of compute clusters without having to wait in a queue. And they were able to essentially do their own drug discovery, treatment/vaccine for COVID. So that gave us a great confidence that, hey, you know what? We are trying to really build a company in that particular space. So since then, Clovertex is really known in the high-performance computing space. But we have started to look at other areas within pharma where we can essentially go and try to improve services. And not only that, over the years, we have done so many of these implementations for various pharma companies, trying to solve the same problem again and again, that we have built a drug discovery platform. So we really sit between the research and IT, where our scientists can talk the science language, and our IT engineers can talk the IT language. And we can essentially provide a platform to the scientists for that. So this platform today is more focused on structural biology, Cryo-EM, but very soon we are going to essentially roll out genomics and multi-omics pipelines on the same platform. Now, when we think about a product or a platform, there are two things which are very important. One is, how do you provide easy access to compute? Not only easy, the right access to compute, which requires a lot of benchmarking. So we'll talk about some of it today. And that's where we have been collaborating with Intel over the last 1 year to benchmark several instances in AWS across various workloads for Cryo-EM. So instead of you having to experiment various instance types and try to figure out over months or a year what's the right price-performance ratio, we can share some of our knowledge. And we'll see some of the results today. The second part is, how do you make the life of a scientist better? There was a chart that Michael had brought up when Michael was talking about the Cryo-EM. It's a workflow that you go through. And a lot of the steps in those workflow are very manual steps that you have to take. And that's where we are partnering with KEK, who are focused on building workflows to automate those steps. And our idea is that, hey, if we can provide an easy way for scientists to get those optimized benchmarked instances along with those workflows, it can really aid a lot of science for them. So HPC certainly is a key area for us. But like I said, we are getting into other areas as well. Some of them are listed here on the slide here. And when we talk about managed services, so whatever we build as high-performance computing, we really manage that as well. And we have grown into other areas of managed services, including cloud managed services and database managed services, where for this one pharma, we are managing today thousands of databases, on-prem, AWS, all flavors of it. But the differentiator that we have is a lot of focus on automation. So when we talk about managed services or managing some instances, you always talk about L1, L2, L3 kind of support, where L1 are those routine tasks, L3 are those complicated tasks. And our motto is that, can we make that L1 as an automation? So within the first year of service at this pharma, we have been able to automate over 80 to 90% of the L1 tasks, which were done manually through now automation. So yes, it's not directly research, but it's still enabling an organization wide across to make their systems up and running. So today in this talk, we'll talk about more around what kind of benchmarking we have done on various Intel instances for Cryo-EM workloads.
Now, yeah.
I'll pass it over to Toshio-san.
No, I think that I can just talk, right?
Yes.
Great. So then thank you. It was really great introduction myself too. So I don't need to talk too much. So I'm from Japan. Actually, it's Tsukuba City near Tokyo. And our facility is called KK. And the English name is High Energy Accelerator Research Organization. Why KK? Because it's abbreviation of Japanese. 高エネルギー加速研究所. So it's a very strange abbreviation, but the KEK is very easy to pronounce, so we use KEK. And our facility is mainly for physics. So we have synchrotron about diameter of 3 kilometers. And it's one of the major synchrotron. And we have also the major facility for beamline facilities. And on top of it, that we have also the Cryo-EM facility. And this facility is open for all the Japanese researchers in Japan as a shared research facility. So main task for me is doing the supporting these users and also developing the software for them. And my own research is algorithm development for the single particle analysis, which is Cryo-EM data analysis part. So the organization consists of two major research institutes, which is particle and nuclear studies, and one is material structure science. And our facility is called, my center I belong to is called the Structural Biology Research Center. And it's a very tiny portion of the KK because the biology is not like major field in our research institute. but we do really the good effort. We have a very, very rich facility for the structural biologists. So now that we have the Cryo-EM facility, we have the Taos Arctica 200 kilovolt, which we operated about 4 years at this point. And then from this year, finally, we got Titan Krios G4, and it's a 300 kilovolt high-end Cryo-EM, and it's coming soon and open for the users. So this is,
Good. Yep. Okay. So basically, what we're going to talk about next is Kshitij is going to talk about some benchmarks because people like benchmarks and that show how reInvent, which is the software that Intel has optimized on for running on Intel CPUs, how it performed in their hands on AWS.
Thank you, Michael. So if you know about Cryo-EM, right, in the last 3-4 years, that's a technology which has really come into light. A lot of pharmas are trying to either use a CRO for the Cryo-EM data or they're building their own Cryo-EM labs. The challenge is these microscopes generate so much of data, terabytes of data. How do you securely you can certainly do it on-prem, processing which a lot of companies do, but how do you take this data securely in time over to AWS, store it, process it? And that's where a lot of these instance optimization really comes in. So here what you see on the chart are 3 instances. We have done several of these, but for the purpose of the conversation, 3 instances that we are looking at. So let me walk you through the chart, how it's set up. So on the left side, you have the runtime in hours. So when we are running a reInvent workload, how many hours is it taking? On the left side, you have the cost of it. Each blue bar represents how much time it took to process the data. So if you look at the first instance, which is a C6i8XL, that instance has 32 vCPUs. So when we run a workload on that instance, it took about 21 hours or so. The orange box is the price per instance. So that instance costs $1.36 per hour in AWS. This is not a price. This is the direct, if you get an instance on demand, that's the price that is here, okay? So orange line shows you that orange box shows you the price per instance. And the line on the top that you see shows you the total cost for running that workload. So looking at our example here, the C6i8XL took 21 hours, and it costed $28 to process that. The next instance that we looked at is a C524X large, which is a 96 vCPU. The cost is $4 some cents. It took 7.5 hours to process for $29. And the last instance that we have here is the C6i32XL, which is a 128 vCPU instance. The most expensive instance here, which is $5.40 or something, and took about 5 hours to process that data. Now, looking at this, right, if I'm a scientist, if I'm trying to pick an instance, and these 3 are presented to me, I would gravitate not to look at the C6i32XL. Oh, it's a $5 instance. It's very expensive. I'm going to go with something cheaper. Michael, if I may have the clicker here.
Yep, go ahead.
So I will go with something cheaper. But if you see the results, okay, the C6i32XL costed the least to finish that workload. It costed $27 to finish. It finished sooner also. Yes, the price per instance is high, but to finish the entire job, it was much faster. So your overall cost was cheaper. So that's the power of benchmarking, right? That is there, that can be leveraged. And like Michael talked about, this is the Intel optimized version of reInvent, and reInvent is I would say, the most predominantly used open source software in the Cryo-EM space, right? So the key point is that the instance with the lowest hourly cost leads to a higher processing time. Now, looking at this scenario, right, you can think about we, along with Intel, we can share this knowledge with you to say, hey, you know what, you may want to evaluate this, or you can learn on your own. So there are several options like this which are available, which have been benchmarked, which we can really bring to it. And that's one thing which the product I talked about essentially does is, hey, gives, based on your workloads that you have, it can make you that recommendation, hey, based on your workload, how much time you want to process, we recommend XYZ instance. We recommend XYZ cluster. Now, you may decide to use it or not, but at least you have a guidance which is available to you, right? So the result is that that your job is at a lower cost, okay? And it's 2 hours faster. If you compare the instances between C524, which is 7.5 hours, and 5 hours between C6, keeping the 32 vCPU instance aside, because that's taking a lot of hours, is that you essentially have an instance which is 33% higher in the cost, okay? But it's faster. It's 7% faster, but the 7% adds up when you think about doing these workloads, right? Several times in a year, and multiple scientists are doing. So this plays a huge role in your overall cost, how you look at your cost for the infrastructure, and from the scientist point of view, how fast can they process and how many structures can they process. There are so many scenarios where you get the data out of Cryo-EM, it runs for hours and hours, you start getting the data, you look at it and you realize, oops, these are not the right settings, I have to restart. So you may have to go back and restart with different set of parameters. So the amount of iterations and repetitions that you have to go through makes these things, these small numbers, really add up to something which is large. And that's the work which we have been doing with Intel for quite some time to benchmark new instances. Today, AWS announced a lot of other instances. We'll go and basically start benchmarking on them to see how those workloads really look like. So a very, very valuable exercise, which I think is a good thing to share.
Right.
Great. So it's my turn.
Or I can change for you. Go ahead.
Thank you. So we also do the benchmark at the KK. And the reason why we started developing the AWS is a user support, which I forgot to tell you guys. So we have about 50 research group we are supporting, and 10 of them are industrial users. And for that many of them just started using the Cryo-EM because since we have the X-ray crystallography facility, many of the users that we support are crystallographer originally, and then they started using Cryo-EM. However, relatively, the Cryo-EM requires a high-end machine, and it's not that easy to get the access to the machine. Therefore, we wanted to support these users more easily and cheaply. So that we decided, okay, maybe the public cloud might be really good idea to use. So we started developing it, but one of the concerns was people always ask me how fast and also how much it will cost. Therefore, we started doing the benchmarking so that we can tell how much it will cost and how much the speed up that you can expect it. So because we are doing the analysis daily, we use a real data set, which is actually this nitrogen redox data, which we process and reach to the 2.85 angstrom resolution. And this one is showing only 2D classification result, but we did also the benchmark with 3D refinement, 3D classification, and polishing, if you know. So there's many other different processing that which we need to do the benchmark from the software for the Cryo-EM, but this is just one result. Okay, so the x-axis is a type of the benchmark. Mainly it's a machine type, and y-axis left side is runtime, and the right side is a cost. Processing cost means that how much it costs to process this particular data set with 2D classification. So before we started working with the Michael and Schutz, and we did our own benchmark and tried to compile the reliance with the optimal setting. And this is the leftmost side is showing the 1.62 hours and $59. And this was very, very expensive for us. So we decided, okay, maybe we have to optimize more. And then at the beginning, we used a C5 instance. And then the Amazon people recommended us to use a C6i, so we started using it. But we couldn't reach to we couldn't get any improvement much. Then we got advice from Intel engineer that maybe that you can change the compiler setting. So we changed the compiler setting. So this is the new one. So the yellow one is new X-core. And the old one, we used to use the X-common setting. And then we got a significant improve here. So the the cost became $60 to $30, so 50% reduction. And also the processing time. Then on top of it, the Intel engineer recommended to change the MPI and thread setting, which is parallel setting for the software that we use called reInvent. And then we got another about 30% reduction, I think. Again, so what we think is key point. So using the right compiler flag can be shorten the runtime and reduce the processing cost. So this is very important, we figured out. And the result is that basically using X-core instead of the X-common. And yeah, it says it provides 3.4 times faster runtime and 3.7 lower cost. Means that the actual cost and the time linearly as correlated, right? The improvement of the cost and runtime. Then the third point is that using MPI thread and all virtual core versus less MPI thread, and mostly physical core yields the shortest time and lowest cost. Means you also have to pay attention for how to run the program. So this was a really great opportunity for me to collaborate with Clovertex and Intel, and we are very thankful for them.
Thank you. So I think that might be our last slide, but this is an important point. I mean, as someone who is a longtime user of AWS from my past company before I joined Intel, I saw firsthand the movement of data from an on-prem system or workloads from an on-prem system to the cloud being done rather haphazardly, and people not fully understanding that even though underneath it all, they're all racks of servers, the way in which you interact with the cloud is often different than the way you interact with an on-prem system, and that you need to just be sensitive to that. Don't blindly port your code, but rather be thoughtful about how you do it. And some of these compiler tunings and price estimation things are important because, as you know, in an on-prem system, the costs are kind of somewhat non-obvious. And in the cloud, everything's got a cost associated with it. So thus, there is a lot of emphasis on what do things cost when I run them in the cloud. And that cost is somewhat hidden in these on-prem systems. So knowing the difference between them is important.